Our first lecture here is on units. And to start this lecture, let's talk about F is equal to ma. And usually in physics, what you have traditionally done is you try to find a numerical value of a force, look at the numerical value of a mass, and find out the acceleration it's undergoing, and you determine the force. However, there's something else very interesting about this equation, and that is the creation of a unit system off of it. Years and years ago, someone determined that there might have been a pound. So they figured out the unit of a pound. Then they figured out the unit of a foot, and then a second. And prior to the existence of Newton's law, everything worked fine. In the marketplace, someone would weigh a good, and someone may measure it and figure out some time which had nothing to do with the marketplace, or people were purchasing things in the marketplace based upon the size and the weight. So up until this point of the creation of this equation, no one paid too much attention to the fact that there may exist a mass, until Newton discovered there's some other item that if you put there, invariably this always equals. So what was the unit that got put there? If you were in this unit system, it turns out it's a slug. Now, what is this unit system? Usually it's called the British gravitational system. British gravitational basically had pounds, and I'll create a little chart here first. Basically had, for its force, had a pound. For its mass, it had a slug, or has a slug. For its length, has a foot, and for its time has a second. So if we create a little chart and look at the units here, get some idea of how things were created. However, let's take a look at the slug, and let's write it this way. Now, when you were in thermo, you came across another system which was not British gravitational. Here's what we'll do here. In thermo, you were dealing with the English engineering system, and it was quite different because someone put a pound force in there, a foot, and a second, and they wanted a pound mass in there. Now, one of the bad things that, and this exists in thermo a lot, and it may have driven you crazy, it may not have, but it wasn't just F is equal to ma, but it was F is equal to ma over some constant conversion. So it depends on how you wanted to look at this. You could have equated this to F is equal to m over g sub c times a. Now, let's take a look at this for half a second. And let's look at here a British gravitational representation and an English engineering representation. First and foremost, the units on the force are the same, and the units on the acceleration are the same. So as a result, you could contend that a slug somehow related to a pound mass over all the g sub c. And as it turns out, the g sub c was nothing more than 32.1 32.174, and it was a mess. Pounds mass, feet, second squared, pounds force. Now, if you take a look at this, okay, so whatever number you put here is going to be the same as the number you put here, and the acceleration is going to be the same as the number you put here. So how many of these is equal to what of these? Well, if you look at it, one slug would force your hand to be 32.2, or sorry, 32.174 pound mass over 32.174 pound mass foot pound force second squared. So this being the case, you can argue that if you put in one slug, it's the equivalent of put in 32 pounds mass. But the conversion between these two takes place directly between this value and this value. But this is a mess, and this is a lot cleaner. As it turns out, fluids almost exclusively uses slugs, and thermo almost exclusively uses pound mass. The only unifying between these two is a unit called SI unit. SI units are the same in either. So let's take a look at SI units for a second. SI unit, the force is a Newton, the mass kilogram, the length meters, and the time is a second. So what happens here, or what did happen there, was that the Newton was generally the derived unit here. What I mean by derived unit is at some point in history someone defined a kilogram, a meter, and a second. And then what they decided is if we have a kilogram, a meter, and a second, then we obviously have to have a force representation. It turns out that through this equation, the Newton was the derived unit in the SI. Turns out in British gravitational, the slug is the derived unit. So it's very often that people will say a British gravitational is a FLT system, in which the mass was derived, and an SI unit is a MLT system, in which the force was derived. I'm not even going to address English engineering because it's not used in the course, and I can research which one was derived. My guess is that this one is the derived unit because in history these two are the same, and previous to F is equal to ma, if you're deriving the slug here, common sense would tell you that this is the derived unit. When I say derived again, I mean derived through Newton's second law. Now, often textbooks will come in and discuss FLT systems and MLT systems, and they'll say this is an FLT and MLT system, but you have to distinguish between what is a system, say FLT, MLT, and a representation. Okay, now here let me give you a distinction between these two. Let's say somewhere in your future in fluids you're going to come across an equation which has a pressure plus a rho and a velocity squared over 2. Now this is coming through Bernoulli's equation, but It'll show up later. Now, you know full well that usually pressure is represented by pounds per inch squared, PSI, and this is usually represented, and if you're in these systems up here, we're going to basically exist mostly in BG system here. You're going to end up with a slug, and we'll talk about what rho is later, but foot cubed, and then feet per second, and then you got to square this. 2 has no units. Now if you take a look at this, you could easily divide this out, turn this into feet, and now what you have is a clashing of units. Okay, now the clashing of units is on this side you see a force over a length squared. What you have here is you have a mass of length squared over a length to the third and a time squared. Now what I'm doing is where I see a foot, that's actually a length. So if I have length foot cubed, I have a length cubed. So these are generic. These are actually specific to a coordinate system. So I'm going to quickly move into from this representation to that. The first problem you've got is if you start trying to match units here, they don't match. So your first inclination is if you carried units through this calculation, say the pressure was some number, say 5, and this was density was 2 and velocity was 5 squared, you'd get numbers, you'd add them up, but the units wouldn't match. Now here's the other beauty of F is equal to ma. This is Newton's second law. It works fine, but think of it as something else. It's a unit converter. Now, here's what I mean. F is equal to mass times acceleration is nothing more than length over time squared. So, if I want to convert something from mass to force, this is how I do it. Again, 2 ways you can do this. What I see here is I see a force here, I see a mass here. Major conflict. So let's say I want to take this and do an FLT representation. Representation of these two equations. So this means anywhere I see a mass, I need to get rid of it. How do I get rid of it? I go straight to F is equal to ma. I alter this equation such that m is equal to F t squared L minus 1. So I simply move the t over and the L under, and this is what I get. F, so I'm using this, simply gets written down as F L minus 2 pounds per square inch or square feet plus, now I have a mass. I basically pull this right here, F T 2 L minus 1, there's my mass, L2, now I'm going to grab the L minus 3, L minus 3, T minus 2. Now this one's easy enough. This is just F L minus 2, but now I need to cancel some things out here. F, I see a 2 here and a minus 2. They cancel. I see a 3 and a 1 and then a 2. So this becomes 2, essentially minus 3 minus 1 plus 2 is equal to nothing more than minus 2. So as you can see, this term basically becomes the same exact units that. This is the FLT representation. let's say we turned and we wanted to do the MLT representation of this. So now let's look at the MLT. Everywhere I see a force, I want to get rid of it. This is F is equal to MA. And now, let's copy this equation down here. Here's the equation copied. Now, it's the same equation that exists up here. I just simply did a copy and moved it down here. So now I need to get rid of the F in there. I basically put in MLT minus 2 over L minus 2. So this is this term. This is the force. Now I start trying to convert out or get rid of these, and I'll see L2, L minus 3, T minus 2. Now you can start taking a look at this. On this side I've got an M, I've got an L plus 1 minus 2, be L minus 1, T minus 2. Now I've got an M. Here I have minus 3 plus 2, L minus 1 and T minus 2. Dimensions match. This is a MLT representation of this equation. Of this equation. Now, why would you do one versus the other? Here's a typical example. Take a look at what we just did. What is this? This is pressure. Pressure is usually thought of as being pounds per square inch or something. So usually somebody tells you a pressure, they walk in, well, they'll say it's 14.7 psi out there. People don't usually walk in and say, well, it's 14.7 slugs per foot second squared. I got that from the mass, the length, and the second squared. People usually don't walk in and say it's 14.7 slugs foot over foot second squared. So the MLT representation of pressure leaves a lot to be desired. It has no real physical interpretation. The FLT representation of pressure has it basically has a simple, easy to understand connotation to it. It's the pounds per square inch. So very often you may be in the MLT system, for example SI, and pressure is represented in the MLT system being SI as being pascals or Newton per meter squared or bars or something like that. But in essence, the physical interpretation of pressure is best suited to an FLT representation, not an MLT representation. This is an MLT system in that that's how it was generated, the system itself, but the FLT representation can change based upon what you're trying to do. Density, for example. Density is usually a mass per unit volume. Well, that's kilograms per meter to the third, or it's slugs per foot to the third. Is there another way to represent it? Well, yeah, this is MLT representation of density. What's the FLT representation of density? Well, you have to go through it, but it's mass. Unit volume is a length to the minus 3, so you've got to convert. And if you want to convert, here, we'll just, F is equal to mass times length times to the minus 2. This is F is equal to MA. which means M is equal to F L to the minus 1 T to the 2. Stick that in there, and what you get is F L to the minus 1 T to the 2 L to the minus 3. So you could think of density as being, okay, L to the minus 4 T squared. It would be like pounds second squared over foot to the fourth. Now, do people usually come in and tell you the density of an object is pounds or Newton second squared meter to the fourth? Do people come in the room and tell you that my density is this and give you those units? Nah, they don't generally do that. They'll generally tell you in units of kilogram per cubic meters or slugs per cubic foot. So again, the representation means a lot. Now to review, basically what you have is an F, M, L, and a T. You're generally not going to mix force and mass in some sort of representation. If you do have them mixed in a representation, you need to convert from one to the other. You may recognize that we're going to mostly be existing in this course in these two units. Traditionally, fluids occurs in BG or SI. Traditionally, thermo exists in EE or SI. Causes some trouble because a lot of the products that you purchase out there can be represented either in one or the other. Go to some of the product catalogs and you'll see that. So that can give you problems in your future. However, for the course that we're looking at, what we're going to operate in is these two. Later in the course, we're going to add another column here, and since T was already taken up, we'll have to use something else for temperature. And this is in, okay, if it's BG, usually it's either degrees Fahrenheit or something like that. It could be Rankine, or anyway, we'll just keep it in F for the moment. And in SI, it's degrees C. Now, temperature is its own unit. It's not convertible. It doesn't exist in F is equal to MA. But for heat transfer, it makes a big deal because most everything is heat transfer. There's temperature measurements and things like that. It's very appropriate that it ends up in the units because, as we will find out in the Buckingham Pi theorem, that heat transfer basically operates the same way fluids through it. So we should include this. However, in the early part of this section, we're not going to. But for completeness, I put it in there.